Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 02, example 02. Student, we have a now new example. As you can see here, let me read the example. Find the cross section of a concrete and area of steel. So this means that this is a design example, right? And required for a simply supported rectangular beam with a span. Noting down this point here that the beam is simply supported rectangular beam with a span of 15 feet, right? So let me write down the data right here. So right, we have a simply supported case, right? We have a span of L equals to 15 feet. That is to carry a computed dead load. The dead load is given, which is denoted by DL, is a 1.27 kip per running feet, and a serviced live load is given 2.44 kip per running feet. Material strengths are FC prime equals to 4 KSI and steel grade is 60 KSI. So this is all about the data, right? And noting down this point here that at this stage, as this is the initial stage and initial examples, in coming example we will include the beam weight in this dead load, but in this example I am ignoring the self weight of the beam, right? So let me find out the ultimate dead load, and what we need in this example, we need B. We have to determine the width of the section, depth of the section, and area of steel which is required. So let us solve the rest of the part. So first of all, we find out WU. So WU is what? 1.2 dead load plus 1.6 live load. So we know about dead load, live load. If you plug all the values, we got the WU 5.926 kip per feet. As the beam is simply supported with a UDL of this much, so we know the bending moment for a simply supported beam is WU L square divided by 8 multiplied by 12 to convert it into kip inches. So it will give us 2000 kip inch, right? So WU is this much, and multiply with L square, that is 15, multiply with 12, we got this is our moment, 2000 kip inch. Now here we need the depth of the beam. We already derived an equation and we know about this equation, that is mu 0.205 FC prime into B. But here I am not using this equation, right? I am not using this equation, and I am choosing the deflection criteria, which we have already discussed this. And let me use this criteria, and we will go for we will go as the conventional way, not using that equation. So for a beam case with a 420 grade steel, that is 420 means grade 60, the coefficient for the depth of the beam is L by 16, which is for a simply supported case. So let's say we are using this coefficient and we will find out the depth. So the depth of the beam. Remember, this coefficient will give you h. So L by 16 times 12. So L is 15 feet multiplied by 12 to convert it into inches. It gives us 11.25 inches, which is, let's say we are rounding this to 12 inches. If we find out the effective depth from this, so 12 minus, now here I'm choosing the effective cover. Let's say it is 2.5 inch. 1.5 is the clear cover and 3 by 8 inch is the stirrup dia. And right, this is how we usually use. Let's say here is my bar, here I have stirrup, so 1.5 inch is my clear cover plus 3 by 8 is my stirrup dia plus here I'm assuming, let's say this will give me 1.875, I think so. So 2.5 minus 1.875, it will give me 0.625. This is, let's say if I assume this bar, let's say I'm using this bar as 11 number 11. So 11 divided by 8, so the diameter of this bar is 11 divided by 8 is 1.375. If we half this, it will give me 0.6875, which is close to this one, right? So the effective cover is to the center of this bar, right? So this is 1.5 inch plus this half, that is 0.687 or 0.625, so it will give me 2.5 inches, right? So that's why I'm using here, I'm supposing that, let's say I'm using number 11 bar, so that's why I'm choosing 2.5 inch effective cover. So this will give me the effective depth of the beam is 9.5 inch. So 9.5 inch is my effective depth. Now let us use this effective depth and find out the area of steel. So area of steel, now let's say I'm using trial and error method. So let's say I'm using 0.2 times of D and it will give me 1.9. So if I calculate my area of steel, this is trial number 01. If I calculate my area of steel MU, 0.9 into Fy into D minus A over 2. So my A is this much and D is this much. So if I plug the value, and MU is 2000 kip inch, right? So I got 4.331 square inches. Now if I use the second trial to check the value of A, so A is Fy 0.85 Fc prime into B. Now I need the value of B, right? So let's say I'm using the B value here. B, let's say this is D divided by 2 and I divide this, let's say my B is 5 inch. So B here will be 5 inch, so it will give me 15.28 square inches. So here we can see A is not coinciding with this value. It get increasing. If you see here, let's say I'm calculating area of steel again. So this time if I calculate area of steel for this value, you will see it will result a negative value with A's. So what does it mean? This point is very important, and that's why I'm using this calculation, and I see so many students do this mistake. This negative value means that the values of B and D, which we choose 5 and 9.5 inches, is wrong. There are two small values. We have to increase this value. We have to increase this value, right? We have to increase this value, right? So this is the key point which I want to show you to you people, that you must understand what this negative value means, right? This is the most important point which almost all students do this mistake. Now let's say here we need to increase the B and D value, but make sure that if you are increasing B and D value, remember your area of steel will decreasing. If you are reducing your B and D value, your area of steel ratio is decreasing, right? Increasing, sorry. So let's say we are using B value is, my B value is 9 inch and my D value is 17.5 inch. Here I am using just the my suppose values. R, we can also obtain the B and D value from steel ratio if we use the maximum steel ratio. Here I'm supposing these values and go for trial and error method, and let's see what where my A values, area of steel value, is coinciding or not coinciding, or consistent or not consistent. I will check whether it give me a negative value or not, right? So this is a way that you can increase your values. Like you suppose with different value, you have to use different trials for B and D, and you will find out your result, that you go for trials and you find out and you see whether your area of steel in which you got in trial 1 will coinciding with trial 2 or not. So this is one way, but the best way is this, that you find out the exact value of B and D. How we can do? We can find out the value of D minimum by using this equation, right? By using this equation. Or we can calculate, as I already discussed this method in example 01, that let's say I'm using rho max, right? We know rho max is 0.75 or 75% of rho B. So my rho B value, that is the balanced steel ratio, I have already derived this equation, which I am writing down here, 0.85 beta 1 Fc prime divided by Fy into 87 in when we are using caps, so we will use 87. If you are using pounds, so we will use 87,000 plus Fy, right? We know all the values, we know, because the Fc prime is 4 KSI, so that why this value beta 1 is also 0.85. So if I plug all the value, I will got my rho B value is 0.0285. This is my balanced steel ratio, and from this I will multiply this value with 0.75, and I got the rho max value is 0.0214. and let's say I'm using this rho max value, and I will find out the value of area of steel, right? So by using this value, I will find the D value by supposing my B value, right? I will suppose this B value and I will find the exact value for D. Now this D will be the ultimate value. Ultimate value it will give me the limiting value, right? Because if I use rho max and rho minimum, right, in which equation, let me write down the equation. We know the equation which we previously used in example 01 prime, right? So we know this equation, and if I use rho minimum, it will give me a value of D, which will it will give me a value of D. And if I use rho max, it will give me another value of D. Now these two values are the limiting values. This one will be the maximum value of depth. This one will be the maximum value of depth, and this one will be the minimum value of depth. This maximum minimum values means that if we are using this maximum depth, right, so if we increase the depth from this value, it will causing the ductility check to be failed, because we will use this ductility check that rho provided will be greater than rho minimum, and it should be less than rho max. We know about this check. We do this in lecture 01 and in various examples. So if we choose a depth which is greater than this depth by calculating the rho minimum, so it will cause that rho p will be less than rho minimum. This is important because we are choosing such a depth which causing minimum steel ratio. So if we use such a depth which is less than this depth, let's say this depth is, let's say this is 10 inches, and we choose the depth, let's say that is 8 inch. So this depth will give me the steel ratio which will be more than rho max, and it will fail this check. So these two depths are the limiting depth. We have to choose, right? This is my D minimum and D max. We have to choose the depth, our required depth in between these two values. If we choose the depth in between these two values, our check, that is rho p ductility check, rho p must be greater than rho minimum and must be less than rho max, will be okay. If we not satisfied, if our depth D is not satisfied these two depths, so this check will be wrong. So this is very important that you find out that such a depth which will pass this check, right? Otherwise you have to revise your design. So let's say we calculate the depth by using rho max value, and we calculate rho max, which is 0.0214. So we will use that above equation, right, this one, and we will find out the D value by supposing the B value divided by 4, right? So we know all the values, and using your calculator we will find out BD square, which will be equals to 2130 square inches. Now let's say we are using B value, let's say we are using 10 inches. So from this the D value will be 14.60 inches. Now the area of steel will be rho times PD. So we know the rho value, that is 0.0214, B value 10 inches, D value is 14.60, and from this we will calculate our area of steel, which is 3.12 square inches. Now if we choose to number 11 bar, it will exactly give us 3.12 square inches from this table. We can see here we are using number 11 bar. So this is my number 11 bar, and if we are using number 11 bar, so here I have 3.12, right? So this is my area of steel. So this is the exact value. So 2 number 11 bar will give me this exact value, right? Now let's say I'm calculating the total depth H. So 14.60 plus, as I'm using 2.5 inch effective cover, so my total depth will be 17.1 inch. So I round my depth, let's say it is equal to 18 inches. Now see the difference. As I'm rounding my depth from 17.1 to 18 inch, it will change my effective depth, because this time if I calculate d minus 2.5, I will got 15.5 inch. So you can see the clear difference that my previous depth is 14.60. so now my depth is increased. So by my depth increase, so if we are increasing the depth will cause decreasing in area of steel. So area of steel will be decreased, right? If we increase the D value, the area of steel will be decreased. Now we need to recalculate the area of steel, right? What will be the exact amount of steel for D is equal to 15.5 inches. So here we have different ways to calculate that area of steel. So let me discuss those ways. The area of steel can be calculated by calculating the rho value, right? If we calculate the rho value by using the same equation so if we use this equation, we got a quadratic equation from this. We know all the values. This is 2000, this is 60, B is 10 inches, D this time is 15.5 inch, and we will find out the rho value from this. So from this, if we plug all the values, we got 0.015 equals to rho minus 8.85 rho square. So we got a quadratic equation, and if we write down this quadratic equation, so this is a quadratic equation, and we clearly see A equals to 0.85, B equals to -1, and C equals to 0.015. Now using the quadratic equation, if we use the quadratic equation, my rho value will be 1 plus minus square root into 1 square minus 4 AC. So my A value is, this is 8.85, right? So this is 8.85 times 0.015 divided by 2A. Use the positive and negative value. So here you can see clearly we got two values. Now what value we have to choose? As you can see, if we compare this value with my rho B, so my rho B value is 0.0285. So this value is more than the rho B, 0.0285. So I will ignore this one, right? I will ignore this one and I will select this one. So my rho value is 0.018. This is my final rho value, and from this I will calculate my area of steel, right? Area of steel will be this time is 2.79 square inches. This is the way that if you change your effective depth, right, if you change the effective depth, as you can see we change the effective depth, because first time for D equals to 14.60, my area of steel is 3.12 square inches. But if as we can change the depth, from 14.60 to 15.5 inches, so now it will give me this amount of steel. So as I already mentioned, that if you are increasing your depth value, it will decreasing your area of steel. If you are decreasing your depth value, as you can see here, we decrease the depth value, our area of steel is increasing, right? So this is a direct relation between D and S. But this is another way. Sorry, this is the first way that you can calculate your area of steel if you change your let's say this is method number 1. But this is a lengthy method. Almost this is a lengthy method, right? We don't go for this method, and we will use the second method, method 2. So method 2 is simple. We use trial and error method, right? We know A equals to 0.2 times of D. If we calculate the A value from this, let me D value is 15.5. Let's say my A value is 4 inches. Now this is trial number 1, right? My area of steel mu divided by 0.9 Fy into D minus A over 2. I got the value 2.743 square inches. Now if I use further trials, let me use trial number 2. So in trial number 2, I got A value, A is Fy 0.85 Fc prime into B. So I know the B value, that is 10 inches. Area of steel will be this one, right? And Fy 60. I got the A value is 4.83, which is close to the previous one. So that why if your A value in the second trial is closing, right? So that why this means that the DA and B value is correct, right? If it not closed, then you can understand that my values are not coinciding. 2.83 this time, right? If I go for another trial, if I go for trial 4th, so you can see here 4 and 5th trials are give me the same results. So that's why my final value of area of steel is 2.85 square inches. This is in another way, and I'm using tool number 11 bar, which will give me 3.12 square inches. This is method 2. Let me use method number 3, which is the most simple one. Method 3. Which here I'm using the direct method. My area of steel 0.8. So this equation directly give me 2.85. It will directly give me this area of steel. So this is the easiest equation. You don't need trial and error. You just put all the values correctly, use your calculator correctly, you will find to the exact amount of steel. We have another method, also another direct method, right? Let me use that method as well. How we can do this? Method number 4. I have already discussed and derived this equation. So my M value is, we can use that R and omega relationship. which is also one of the way that can be used for determining the rho value, right? So this time I'm using this equation, right? M is Fy divided by 0.85, and if you note it in that equation, omega is 0.85 Fc prime divided by Fy. I think so, right? And here, right, kif inch, KSI, right? This value will be in PSI, sorry, because I'm using 2000 KSI, sorry. This value will be in KSI. Now this time, if I plug the R value, M value in this equation and I use my calculator, I got the rho value is 0.0184, right? And if I calculate my area of steel, rho times BD, so the rho value is this one, B is 10, D is 15.5, I got 2.85 square inches. So this is another way that you can calculate your required area of steel. So we have different methods: direct method, tabular methods, graphical methods, so many ways. Quadratic equation can be used, as I already explained, and I can calculate the values of area of steel. So finally we got the B value, which is our requirement, right? So my final value is 10 inch, my D is 15.5 inch, and my area of steel is 2.85. This is our requirement in this example, right? And if I draw my section of the beam, so I choose number 11 bar. So this will give me an area of steel which is 3.12 square inches. My width of the section is 10 inches and depth of the section is 15.5 inches, and the effective cover, we can calculate the effective cover, but we can calculate if I assume the 3/8 inch dia, and this is my number 11 bar. So if I use 1.5 plus 3/8 plus 11 divided by 8 divided by 2, so from this I can calculate my effective cover, which is 2.5 inch. So this is okay. So my effective cover is 2.5 inch, and this is the final design, right? We can check, we can review this problem as we did in lecture 01, in example 01, example 02, example 03, how to check this design. Checking means we have to check the design capacity, that whether our design capacity, that is MD, right, is more than MU, or this is RMD. So we'll find MD and we will check whether it is more than 2000 psi or not, KSI, sorry, kip inch, right? We can adjust, we can find out the value of P by finding the epsilon T value, and similarly we can use another check, that is my rho P is greater than rho minimum and less than rho max. So this is also a ductility check. We have to check our capacity, our strength reduction factor. So, and similarly we can check our S provided is greater than S minimum. This criteria is already satisfied because we have sufficient width, and S max. So in coming example we will use this kind of checks as well, but in the present example we just need B and D in area of steel. Thank you for watching. See you in next lecture.